Look at your hand right now. Hold it out in front of you and then let it drop there. You just watched the most familiar thing in the entire universe, and I'm going to spend the next hour convincing you that you have no idea what just happened. None of us do. Not really. We have a name for it, and the name fools us into thinking we understand it. We call it gravity, and because we have a name, we stop asking questions. That is the oldest trick the human mind plays on itself. It mistakes a label for an explanation. So I want to start by taking the name away. Forget the word gravity for a moment. What you just saw was this. A piece of you, made of atoms, decided without any string, without any contact, without anything touching it, to move toward the center of a ball of rock, 8,000 miles across. A ball whose center you will never see, that your hand has never met, that exerts no visible influence on anything. And it moved exactly, precisely, in the direction of that center, accelerating the whole way, every time. It has never once failed. You could do it a billion times, and it would work a billion times. And here's the thing I want you to sit with before we go one step further. Nobody on this earth, not me, not anyone, can tell you with certainty what reached across that empty space and pulled. That is not poetry. That is the honest state of the science. And I think it is the most exciting sentence I know. Now, you are going to be tempted to say, come on, we solved this. Newton solved this 300 years ago. And I want to be fair to Newton because what he did was one of the supreme acts of the human intellect, and I will defend it against anyone. But I also want to tell you something that the textbooks tend to whisper rather than shout. Isaac Newton himself did not believe he had explained gravity. He believed he had described it. There's a world of difference between those two words, and the entire story I want to tell you tonight lives inside that difference. Let me lay the first brick. Let us actually go back and do what Newton did, because if you skip the steps, you will never feel the force of it. In the years around 1666, a young man barely out of his teens is sitting at his mother's farm in the English countryside because the plague has shut down the universities, and there is an apple tree. Now, the apple did not hit him on the head. That is a fairy tale, and Newton would have been annoyed by it, and so am I. What actually happened is gentler and far stranger. He saw an apple fall. Perhaps he simply watched it. Perhaps he was told about it. He recounted the story differently over the years, and he asked a question that nobody had thought to ask in quite this way. He asked, how far up does this reach? The apple falls from the branch. Fine. What about from the top of the tree? Still falls. From a tower? From a mountaintop? And then the leap that made him immortal. What about the moon? Why does the same pole that drags the apple down not also drag the moon down? And the answer he worked out, the answer that took him 20 years to fully nail down and publish, is that it does. The moon is falling right now. The moon is falling toward the earth at this very instant, and it has been falling for 4.5 billion years, and it never gets any closer. Sit with that, because it sounds like nonsense, and it is the literal truth. The moon is moving sideways so fast that as it falls toward us, the Earth's surface curves away beneath it at exactly the same rate, and so it keeps missing. An orbit is not a thing held up in the sky. An orbit is a perpetual, beautiful, never completed fall. The astronauts who circle the Earth are not in some magical zone beyond gravity's reach. Gravity up there is nearly as strong as it is in this room. They are weightless for one reason only. They are falling continuously, and so is their spacecraft, and so they fall together, and falling together feels like floating. Remember that. Falling together feels like floating. We are going to come back to that sentence, and when we do, it is going to tear the floor out from under everything. Newton took this insight, and he made it quantitative, and this is the part where I lose patience with people who think mathematics is cold. He found that the pull between any two objects depends on their masses multiplied together and on the distance between them, but not the distance 1 over the distance squared. Double the distance and the pull drops to a quarter. Triple it and the pull drops to a ninth. Why squared? Why exactly 2? Because, and this is gorgeous, because we live in 3 dimensions, and the influence of a mass spreads out over the surface of an expanding sphere, and the area of a sphere grows as the square of its radius. The geometry of space itself is hiding inside that little exponent. The number 2 in Newton's law is space whispering to you about how many dimensions you live in. Nobody designed it that way for elegance. It is just true, and its truth is bottomless. Now, here's where it gets strange, and I promised you it would, and I keep my promises. Newton's law worked. It worked so well, it is almost embarrassing. It put the planets in their places. It predicted the return of Halley's comet decades in advance. Halley, his friend, did not live to see it return, but it came right on schedule, a dead man's prediction kept by the cosmos. In 1846, astronomers noticed that Uranus was not where Newton's law said it should be. It was being tugged off course. Instead of throwing out the law, they trusted it so completely that they did the mathematics backward and said there must be another planet out there of this mass at this position doing the tugging. They pointed the telescope where the equations told them to point, and there was Neptune, a planet found on the tip of a pencil before any eye had seen it. That is the power of Newton's description. And yet, when you ask Newton the simple question, how does the sun reach across 93 million miles of nothing and hold the earth? Newton refused to answer. Not because he was lazy, because he was honest. He wrote a phrase that I want you to carry out of this room. Hypotheses non fingo. I feign no hypotheses. He was saying, I will not make up a story to comfort you. I can tell you exactly how strong the pull is, exactly where it points, exactly how the planets will move for 1,000 years. But what it is, what crosses that void, I do not know, and I will not pretend to know. In his private letters, he was even more raw. He called the idea of one body acting on another across empty space, with nothing in between, so great an absurdity that he believed no competent thinker could ever accept it. The man whose name is synonymous with gravity thought his own theory was, at its heart, absurd. He knew he had described the dance without understanding the music. So there we sat for 200 years. A perfect description sitting on top of a complete mystery, and most people were content because the description worked, and working is seductive. But it bothered the right people. It bothered them in their bones. Now here is where it gets strange again, and this time it stays strange. Because the man who cracked it open did not start with telescopes or planets or falling apples. He started with a single, almost childish thought, sitting in a patent office in Bern, Switzerland in 1907. A clerk reviewing applications for electrical devices, who later called it the happiest thought of his life. Albert Einstein imagined a man falling off a roof. That is the whole experiment. A man falling before he hits the ground. And Einstein realized something that everyone before him had walked straight past. The falling man does not feel his own weight. If he let go of his keys mid-fall, they would not drop away from him. They would hang in the air beside him, falling at exactly the same rate, motionless relative to his eyes. For that man, in that moment, gravity has vanished. He has every right to believe he is floating peacefully in deep space, far from any planet. Nothing he can do, no experiment he can perform inside his falling frame will tell him otherwise. Falling together feels like floating. I told you we would come back to it. Hold on, because Einstein turned that observation into a hammer and broke the world open with it. He flipped it around. He said, suppose you wake up in a sealed box, no windows. You feel yourself pressed to the floor, your normal weight. Now, are you standing on the surface of a planet with gravity pulling you down? Or are you in deep space, far from everything, in a box being dragged upward by a rope at a steady acceleration so that the floor rushes up to meet you and pins you in place? And the staggering answer is that there is no experiment, none, that you can perform inside that box to tell the difference. Drop a ball, it falls the same way in both cases. Shine a beam of light across the box, it bends downward by the same tiny amount in both cases. Weigh yourself, identical. Gravity and acceleration are not similar, they are not analogous. They are, as far as the laws of physics are concerned, the same thing. This is what we call the equivalence principle, and it is the seed of everything. And once you accept that gravity is indistinguishable from acceleration, you are forced, kicking and screaming, into a conclusion that overturns Newton entirely. Because watch what happens. If you shine a flashlight across that accelerating box, the light travels in a perfectly straight line through space. But during the time it takes to cross, the box has moved up. So the beam strikes the far wall a little lower than where it left. From inside the box, the light appears to curve. Now invoke equivalence. If light bends in the accelerating box, it must bend under gravity too, by exactly the same amount. Gravity bends light. But light has no mass for gravity to grab in Newton's sense. Newton's law has nothing to say to a massless ray of light. So how is it being pulled? It isn't. Here is the answer, and it is the most beautiful idea any human being has ever had, and I do not say that lightly. The light is not being pulled. The light is going perfectly straight. It is space itself that is bent. The light is faithfully following the shortest path it can, doing nothing but traveling straight ahead, but the straight line it follows runs through a space that mass has curved underneath it. There is no force. There never was a force. There is only geometry. Let me build this brick by brick, because it is too important to hand you all at once. We have been talking about space, but Einstein's real subject was space-time, space and time woven into a single fabric, 4 dimensions stitched together, where what you measure as a distance and what you measure as a duration are two faces of one thing. And his claim, the whole of his general theory of relativity, distilled into one sentence by the physicist John Wheeler, is this: matter tells space-time how to curve, and curved space-time tells matter how to move. That is it. That is the engine of the cosmos. The sun does not reach out and grab the earth. The sun sits in space-time and it dents it, the way a heavy ball sits on a stretched trampoline and makes a valley around itself. And the earth, moving through that valley, simply follows the natural contour of the curved surface. It rolls around the rim of the dent the sun has made. There is no rope, no pull, no action across a void. There is just a planet going straight ahead through a space that has been bent into a curve. The mystery that Newton called an absurdity, the action across empty space, Einstein dissolved by saying the space was never empty and never flat. It was shaped, and the shape is the gravity. Now I have to be honest with you, because honesty is the only thing I have ever had to offer. And the trampoline picture is a lie that tells a truth. It is a crutch. Every time you see that rubber sheet with a bowling ball, a small part of your brain quietly cheats, because the ball only rolls into the dent on the trampoline because gravity is pulling it down toward the floor. We have explained gravity using gravity. It is circular, and I want you to know I know that, because I will not insult you with a picture and pretend it is the real thing. The real thing has no down for the sheet to sag into. The real curvature is the curvature of 4-dimensional space-time. And the dimension that does most of the work is not space at all. It is time. The reason you are pressed into your chair right now, the reason the apple fell, is overwhelmingly because time runs at different rates at your head and at your feet. And matter, when it moves through time, naturally drifts toward where time runs slower. You are falling through time, and the falling feels like weight. That sounds insane. I know it sounds insane. So let me prove it to you, because here is where it gets strange in a way you can hold in your hand. Einstein's theory makes a flat prediction. A clock deep inside a gravitational field, closer to a massive body, ticks slower than a clock far away. Naught appears to tick slower. Time itself runs at a different speed depending on where you stand in gravity. Your head, right now, is aging very slightly faster than your feet, because your feet are deeper in the Earth's gravitational well, where time crawls just a hair more slowly. Over a lifetime, it amounts to a few billionths of a second. It is real. It has been measured, and you do not have to take it on faith from a man on a stage, because you are carrying the proof in your pocket. The satellites of the Global Positioning System orbit 12,000 miles up. Up there, far from the Earth's mass, time runs faster than it does on the ground. The clocks aboard those satellites gain about 38 millionths of a second every single day relative to us. 38 microseconds. Nothing, you would think. But those satellites work by timing radio signals to billionths of a second, because light travels a foot in a billionth of a second, and your phone finds your position by comparing those exquisite timings. If the engineers had ignored Einstein, if they had assumed time is time everywhere, the errors would pile up at a rate of about 7 miles per day. By lunchtime tomorrow, your navigation would place you in the wrong city. Every time that little blue dot finds you on the map, it is because we built Einstein's curved time into the machinery, and it works. You are not trusting relativity. You are using it constantly without thanks. The strangest idea in physics is the quiet servant of your morning commute. But I can hear the skeptic in the back of the room, and I want you to know I love that skeptic, because for most of my life I have been that skeptic. You are thinking, this is all very elegant, but elegance is cheap, and the history of human thought is a graveyard of beautiful ideas that happen to be false. How do we actually know any of this is true? When did it stop being a gorgeous story and start being science? I can give you the exact morning, the 29th of May, 1919. There was a total eclipse of the sun, and a British astronomer named Arthur Eddington had hauled his instruments to a tiny island called Principe off the coast of West Africa, while a second team set up in Brazil. They were there to do one thing. Einstein's theory had made a hard, specific, falsifiable prediction. Starlight passing close to the sun should be deflected by the sun's curved space-time, bent by a precise angle, and crucially, an angle twice as large as anything Newton's old theory could ever allow. The only time you can see stars sitting right beside the sun is when the moon blots the sun out. So they waited for the eclipse, and in those few minutes of false night, they photographed the stars near the darkened sun, and they measured whether those stars had shifted from their ordinary positions. And they had, by Einstein's amount, not Newton's. The starlight had bent. Space had curved. The next morning, the news went around the world, and an obscure clerk-turned-professor became, overnight, the most famous scientist alive. His face in every newspaper on Earth. Now I owe you the honest footnote, because I always will. Eddington's measurements were crude. The error bars were uncomfortably large, the photographic plates were warped by the heat, and some of his data was messier than the triumphant headlines let on. There are historians who argue, with some justice, that Eddington believed in Einstein before the plates were fully developed and saw what he hoped to see. But here is the thing about science, the thing that makes it the most honest enterprise our species has ever built. It did not rest on Eddington's faith. The experiment was repeated and repeated and refined with better instruments and colder rigor, decade after decade, and every single time the answer came back the same: the light bends. Einstein was right. The skeptic in the back was satisfied not by eloquence, but by evidence, which is the only thing that has ever earned the right to satisfy anyone. Now, here is where it gets strange, and I want to slow down, because this is the part that took even the experts decades to swallow. We have a theory that says mass curves space-time. So what happens if you take the curving to its limit? What if you squeeze a star down small enough, dense enough, that the curvature becomes so severe that even light, the fastest thing there is, following the straightest path it can, cannot climb back out? You get a region of space-time folded so steeply that all paths, every possible direction a thing can move, lead inward. Not most paths, all of them. There is no direction left that points away. We call this a black hole, and I want to dismantle the cartoon version right now, because the cartoon is wrong and the truth is stranger. A black hole is not a cosmic vacuum cleaner that goes around sucking up the universe. If we replaced our sun with a black hole of exactly the same mass this instant, the Earth would not get pulled in. It would keep orbiting in the exact same path, in the cold and the dark, because the gravity at our distance would be precisely unchanged. A black hole only devours what comes too close. What makes it terrible is not appetite, it is geometry. It is a place where the curvature of space-time has become a one-way door, and the thing on the far side of that door, the event horizon, is not a surface, not a wall, not made of anything. It is simply the boundary beyond which every road leads down and none lead back. When Karl Schwarzschild first found the exact mathematics of this, in 1916 he was a German soldier on the Russian front in the First World War, working out Einstein's equations between artillery calculations in the freezing mud, dying of a disease he had caught in the trenches. He mailed his solution to Einstein and was dead within months. He never knew what he had found. He thought it was a mathematical curiosity, an idealization. It would take half a century for physicists to accept that these objects are real, that the universe is full of them, that there is one with the mass of 4 million suns sitting at the center of our own galaxy, and that everything in the Milky Way, including us, including you, is in some vast and patient orbit around it. We are circling a darkness we cannot see, held by the bending of a space we cannot feel, and we go about our day. And at the very center of that black hole, the mathematics does something I have to be honest about, because the honesty is the whole point. The equations say the curvature becomes infinite, a singularity, a point of zero size and endless density. And every physicist worth their salt knows that when your equations spit out infinity, the equations have not found a truth. They have found the edge of their own validity. They are telling you, in the only language they have, that they have broken down, that something is happening here that this theory cannot describe. Einstein's gravity, the most successful theory of the large universe ever built, hands you a black hole, and then, at its very heart, confesses that it does not know what it is talking about. That confession is not a failure. It is the most important signpost in modern physics, and it points toward the thing we still do not have. Now, here is where it gets strange in the most recent way, the way that happened within the span of a single human career, and I find it almost unbearable how beautiful it is. Einstein's theory predicted that if you take massive objects and accelerate them violently, say two black holes spiraling into each other, they will shake space-time itself, sending out ripples, waves in the fabric of reality, spreading outward at the speed of light, stretching and squeezing every distance they pass through, gravitational waves. Einstein predicted them in 1916 and then spent years doubting they were real, going back and forth, because the effect was so absurdly, hopelessly tiny that he was convinced we could never detect it. And he may have privately thought we never should. He was nearly right. The stretching these waves produce by the time they reach us is smaller than you can imagine, and then smaller than that. To catch one, we built machines with arms 2.5 miles long, and we measured the length of those arms with laser light, looking for a change in length. And the change we were looking for was about 1/10,000th the width of a single proton. A proton, the thing inside the atom, 1/10,000th of its width across 2.5 miles. That is like measuring the distance to the nearest star and detecting a change the width of a human hair. And we did it. We caught one. Two black holes, each about 30 times the mass of our sun, in a galaxy more than 1 billion light years away, had spiraled together and merged into one in a final instant, releasing more energy than all the stars and all the galaxies in the observable universe combined, shining for a fraction of a second, not in light, but in pure gravity, in the trembling of space-time itself. That wave traveled for more than 1 billion years across the dark, through the whole reach of cosmic time. Life had barely crawled out of the oceans on Earth when it set out, and it washed over our little planet. And we had just barely, in the nick of cosmic time, built the instrument to feel it. We heard two dead stars collide before there were eyes on this world to see them form. If that does not move you, check your pulse. And gravity does not stop at the edge of a black hole or the rim of a solar system. Pull the camera back, all the way back, until whole galaxies are specks of light, and gravity is the architect of everything you see. It gathered the first hydrogen out of the formless dark after the birth of the universe, pulled it into knots, lit the first stars, herded those stars into galaxies, and strung the galaxies themselves into vast luminous filaments. A cosmic web wrapped around immense bubbles of emptiness, the largest structure in existence, and every strand of it spun by gravity over 13 billion years. But when we look closely at that handiwork, gravity hands us a mystery I cannot walk past. In the 1970s, an astronomer named Vera Rubin, a woman in a field that did not bother to make room for women, who worked for years without a fraction of the recognition she had earned many times over, measured how fast the stars orbit at the outer edges of spiral galaxies. By Newton, by Einstein, by every law we trust, those outermost stars should drift slowly because there is so little visible matter out there to hold them. They did not drift slowly. They raced. They moved as though there were 5 or 10 times more mass in those galaxies than all the stars and gas and dust. We can actually see an enormous invisible scaffolding announcing its presence. The only way it can, through its gravity and through nothing else. We call it dark matter, and that name, like the word gravity itself, is a confession wearing the costume of an answer. We do not know what it is. We have never held a piece of it in a laboratory. We know it is out there only because we can feel it pulling, exactly the way astronomers felt Neptune before any eye had found it. A quarter of the entire universe is built from a substance we have named and cannot identify, and we caught it by trusting gravity. And then, at the very end of the century, gravity delivered the cruelest twist of all. We had always assumed that the combined gravity of all this matter, dark and visible together, must be gently slowing the expansion of the universe, drawing everything back toward everything else, the way a ball thrown upward slows as it climbs. So we went out and measured it, and we found the opposite. The expansion is not slowing down, it is speeding up. Some property of empty space itself is pushing the universe apart faster and faster, overpowering the gravity of every star and galaxy and shred of dark matter there is, and we call that dark energy. And it makes up most of the universe, and I will be straight with you the way I have tried to be straight with you all night. We understand it even less than we understand dark matter, which is to say we do not understand it at all. Gravity, the thing we thought we had finally tamed, turns out to be locked in a contest across the whole cosmos with a darkness we cannot name, and at this moment, the darkness is winning. So let me take stock, because we have climbed a long way from a falling hand. We have a theory of gravity that is not a force but a geometry. It curves light. It slows time. It runs your navigation. It builds black holes. It ripples across 1 billion years, and we catch the ripple. By every test we have ever devised, over a century of trying to break it, Einstein's general relativity has not put 1 foot wrong. It is, by some distance, the most precisely confirmed idea in the history of science. And now I have to tell you the part that keeps me up at night. Because for all of that triumph, we are, in a deep sense, exactly where Newton was. We have a magnificent description, and we do not have the explanation. We do not know what gravity is. Let me give you 2 reasons I lie awake, and I am not being modest, and I am not being theatrical. These are real wounds in our understanding, and anyone who tells you they are nearly healed is selling you something. The first is this: there are, as far as we can tell, 4 fundamental forces that run the universe. 3 of them, electromagnetism, and the 2 nuclear forces that operate inside the atom, speak the same language. We have a single gorgeous quantum mechanical framework that describes all 3, that treats them as the trembling and exchange of tiny packets, particles flickering in and out of existence. And that framework predicts the results of experiments to 11 decimal places. 11. It is the most accurate theory humanity has ever produced, and gravity will not join the club. Every time we try to write gravity in that quantum language to ask what happens to space-time, not in the smooth grandeur of a solar system, but down at the impossibly small scale where everything quantum becomes a storm of uncertainty, the mathematics explodes. We get infinities, and not the polite kind we know how to tame. We get nonsense. The two greatest theories in all of physics, general relativity for the very large and quantum mechanics for the very small, are each fantastically successful in their own kingdom, and they cannot stand to be in the same room. They contradict each other, and the universe does not contradict itself. The universe is whole, which means one of our theories, or both, is wrong at the deepest level, and we do not know how. Somewhere out there is a single theory of quantum gravity that contains them both, and finding it is the great unfinished business of physics, and we have been hunting it with our best minds for the better part of a century, and we are not there. I want you to feel the size of that gap. The thing pinning you to your chair, the most common experience of your entire life, is precisely the thing our physics cannot reconcile with itself. And here is the second wound, and it is even closer to home. Gravity is absurdly, ridiculously weak. I know that sounds wrong, because gravity feels like the strongest thing in the world. It holds you down. It keeps the moon in the sky. It crushes stars into black holes. But consider this. Take an ordinary magnet, a little one off your refrigerator, and hold it over a steel paperclip. The paperclip jumps up to the magnet. Stop and think about what just happened. The entire Earth, all 6,000 billion tons of it, is pulling that paperclip down with all the gravity it can muster, and a magnet you can hold between two fingers beats it. The whole planet defeated by a trinket. The electromagnetic force is stronger than gravity, not by a little, not by 100 times, but by a factor of 10 followed by 36 zeros. Gravity is, by an almost incomprehensible margin, the runt of the forces, and nobody knows why. Why is gravity so pathetically feeble compared to everything else? It is one of the deepest unanswered questions we have, and the honest answer, the only honest answer, is a shrug. We do not know. And I find that I do not want it healed too quickly. This is the part where I differ from people who crave certainty, who want the universe wrapped up and finished and handed to them with a bow. I find the not knowing not frightening, but exhilarating, because the not knowing is where the universe is still talking to us. A finished science is a dead science. Every one of these mysteries is an invitation. And I have spent my life accepting invitations, and I have been wrong more times than I have been right. And the times I was wrong taught me more than the times I was right. I have changed my mind in public, which physicists are supposed to find embarrassing, and which I have always found to be the entire point. The willingness to be shown you are wrong is not a weakness of science. It is the beating heart of it. It is the one thing that separates it from every other way human beings have ever tried to know the world. So let me bring us back down to your hand, to the apple, to the simplest thing. You came in here tonight knowing what gravity is. It is the thing that makes stuff fall, and you are going to leave knowing less than you thought, and I consider that a gift, the greatest gift I know how to give, because here is what we have actually learned, that falling is not falling. It is the most natural motion in the universe, an object simply coasting straight ahead, undisturbed, through a space-time that mass has sculpted into curves. That the pull you feel is time itself, flowing at different rates above your head and below your feet, and your body drifting always toward where the river of time runs slow. That the planets are not held, they are released, set free to follow the valleys carved by the Sunday. That the whole magnificent clockwork of the heavens is not a machine of ropes and forces, but a landscape, a geometry, a shape, and we are not standing on top of that shape. We are inside it, woven into it, are every atom part of the same curved fabric that bends the starlight, and that we, this brief arrangement of stardust that learned to ask questions, have stood on one small rock and worked all of this out, the falling moon, the bending light, the slowing clocks, the colliding black holes a billion years gone, and that we have done it knowing the whole time that at the very bottom of it, we still do not understand the thing we have described. We are Newton's children. We have inherited his magnificent description and his magnificent confession in equal measure. So I will leave you not with an answer, but with the question I cannot put down, the one I want you arguing about in the car, lying awake tonight, turning over for the rest of your lives. We have measured gravity to a precision that staggers the imagination. We have caught its faintest whisper across a billion years of darkness. We have built our civilization on top of equations that have never once failed us, and we cannot tell you what it is. The most familiar force in your life, the one you have felt without pause since the instant you were born, the one that will hold you gently to this earth until the day you die, is the single greatest unsolved mystery in all of physics. You have felt it every second of your existence, and not one of us knows what it is. Now go home and look at that hand again and tell me you understand it. I dare you